Yep.
All right. So I know a lot of you guys already, but just to introduce myself to people who haven't interact with me. My name is Kurt Butler. I was an undergraduate in the M&T department here, and now I'm currently a PhD student in the Department of Electrical Engineering, primarily because I'm interested in doing research that's related to computation and machine learning and stuff of that nature. So I kind of get to more actively work on that stuff in the engineering department. So today I'm kind of giving you introduction to something that's like my bread and butter. It's a topic called signal processing, and it's a mathematical framework for how digital systems and electronic systems process information. I think sometimes when people talk about there being applications for math, they can sometimes be very explicit, or other times they can be by analog. You don't actually work with the set of real numbers when you do calculus on a computer. You work with some approximation of that. In the context of what I'm going to talk about, this is something that gets implemented kind of literally, and for that reason I think it's something that's something interesting to kind of give a mathematical formalism to. So the topic is called digital signal processing, and the most appropriate way to kind of introduce that is to start with what you would define to be a signal. So in general, a signal is just any kind of information that varies with time. So if you imagine looking at what the readings on a thermometer are, or the voltage on a piece of wire, or what the position is of a particle that's moving around in some kind of system, you can always take measurements that vary with time, and as you take measurements that vary with time, you'll get some kind of waveform out of it. And this is the essence of signal processing, is that a signal is anything that creates this kind of waveform in time, and you're interested in extracting useful information from it. Now, in the name of the talk, I mentioned specifically digital signal processing. So if you consider signals that are defined in this way, time can be any real number. You have an entire continuum's worth of time values to pick from. In digital signal processing, you are looking at what a computer might see. So the computer has to take individual measurements and kind of work with those sequentially. So if you imagine that I have a computer here and it's second 1 it takes a measurement, second 2 it takes a measurement, you get a sequence of values. So those sequence of values might correspond to actual points on a waveform that you're measuring. But what you see in the end is that you're going to see some kind of discretized waveform. You're going to see just these points in between, but only defined at different integers. So maybe this is time step 0, time step 1, 2, etc., and so on. The typical way of drawing this is with this dot and stem going down, just as a convention. So we want to formalize what it means to talk about things that look like this. So in the same way that a signal in continuous time might be just a function of time, a signal in discrete time is a function of, well, whatever we're plotting here. We're plotting integers here. So it's appropriate to say that a signal in discrete time is just a sequence, or a map from the integers to whatever field we're working in. So you can talk about real valued signals. Those usually have a pretty explicit physical interpretation. It is the temperature, it is the voltage. If you talk about complex signals, you get a little bit more generality. You have to care a little bit less about like the nature of the arithmetic you do. And oftentimes there is like some kind of interpretation for what a complex number means. You know, you have an imaginary part. What does that mean for a physical measurement? Based on the context, you actually will generally have some kind of intuition for what this means. It appears. So, a signal that is defined with domain in the integers is called a discrete-time signal. I'm just going to notate that with dt. So, it helps to define a few signals in discrete time up front, just so we can kind of reuse them later without worrying about what they mean. So, the first signal that we're concerned with is called the impulse. So the impulse is just simply one of these blips in the diagram. And you can define that as just 1 if the time equals 0, and 0 at all other discrete time values that you can give it. So if you draw what the graph looks like for this thing, you have this 1, and everything else is 0. You can define a unit step. And this guy is defined to be 1 for any positive or non-negative time, and 0 at any other time. So when you draw the diagram, it looks something like this. And then just any sequence that I can define, any function, is a perfectly good signal, but you know, these two are going to be useful to have kind of up front. So if I'm not putting any constraints on what it means to be a complex value discrete time signal, then any such function is going to be an okay signal. So if I want to consider these settable discrete time signals, well, it could be any mapping with those sets. So it's just a set of all such functions. Now, a somewhat common exercise that you might do in linear algebra or other algebra classes is considering what the structure, like algebraic structure of a set of functions into a space looks like. So in the set of complex numbers, you can add things, you can multiply things, and these operations carry over into this idea of signals. So in the same way that you define like component-wise addition in a vector space, we define addition like this for signals in any time set. It works the same way in continuous time. So if I have two discrete time signals, x and y, you can assert that their addition is just defined component-wise. And it's also helpful to define scale multiplication. So for any beta that I pick that's in C, I can scale a signal just by, well, scaling each evaluation. So you get a new map, it's pretty much what you would expect it to be. In the same way that I define addition, I can define multiplication. But in particular, we care about these two operations because these give us a vector space. So you can go through and verify all the vector space axioms. They kind of fall out of the fact that C on its own is a complex value vector space, and then giving it each individual time component doesn't matter because all these operations are defined in sense at each point in time. So it's like you have an infinite number of coordinates in your vector space.
Would this be an infinite dimensional?
Yes.
Ooh.
So you have a countable number of components in the vector space. So we have this idea that discrete signals, digital signals, form a vector space. Now, in general, whenever you have an algebraic structure in space, you're concerned with mappings on that space, ways of transforming elements of that space that preserve that structure. So I'm going to erase the notifications. So we want to talk about transformations of signals. So you want some kind of way of taking a signal and putting it into a box and getting out a different signal that is, well, still a signal. And special properties will kind of follow what we want from this box. So in general, this mapping is called a filter. Just anything that you take in a signal and you spit out another signal. So I mentioned that because they form a vector space, we're going to be concerned with specifically linear filters. And before I get into the other big property that we're going to care about, it's going to be helpful to just show a couple of examples of what like a filter can do. So suppose we just take x to be the input signal. We can define a filter that just takes whatever the value of x is at a given time and squares it. This defines a perfectly good filter. Whenever I have some input signal here, the output is just the same thing squared. So the amplitude changes. You can consider scaling the signal by constant gain. So if I have a 1 volt sine wave, the output is a 3 volt sine wave. Now, there's a kind of important filter that is a little less trivial. These things kind of very easy to think about, but something that is not so easy to think about is the idea of, well, what if I don't want to do anything to the signal? What if I just want to delay it by a certain amount of time? So if I have some signal, x, say that I want to take this signal and I just want to delay it by 1 step at a time. So maybe it's 0 beforehand, then if I go over 1 point in time, this thing should be up, this thing should be down, and then it looks the same again. So we want to describe this relationship mathematically where I shift it over by 1. Well, if I decide that this is time 0, then I see that, well, at time equals 1, y of 1 needs to equal what x was at 0. If I look at time 2, y of 2 needs to be what x was at time 1. And so, if you follow the pattern here, y at any point in time needs to be equal to what x was at that time minus 1. So, if you want to define what the filter is doing, h, you just say, okay, well, h is the filter that maps the signal x at each point in time to whatever x was 1 time unit beforehand. And so this operation is called a delay. In this case, we delayed by 1 time unit, but in principle, you can delay by an arbitrary number of time units. And we denote that by delta k. So delta k is simply this filter that, when applied to a signal, gives you that signal at t minus k. Okay? here. You can also think of a filter that just multiplies your signal with another signal. So I'll take the unit step signal that I defined before and I'll say, all right, what if we have a filter that just multiplies your input x with the unit step? Just say, okay. Now, there's two properties that we care about for the purposes of the talk. One is going to be linearity, which is just the idea that h distributes over sums and distributes over scalar multiplications. If you want to do that in one step, you just show that this expression equals x plus b times. This expression equals hx plus b, or beta, times hy. It distributes over the sum and distributes through the scalar multiplication. That is like your one-stop check for linearity. So the other property that we're concerned with is called time invariance. So time invariance stems from a kind of familiar idea. So you can imagine that you have like a voice changer toy. One of those like Darth Vader masks that you press the button and it makes your voice sound all weird, right? So for the Darth Vader mask, you have your input signal, which is just what your voice is doing. And it distorts your voice and it gives you some kind of new voice at the output, called Y. So that's what the action of the filter is doing. Now, you can imagine that maybe I'm playing with this at like 3 o'clock. Now, if I wait a few hours before playing with my toy and I start playing with it at 9 o'clock, you would expect that the voice changer does the exact same thing to my voice that it would when I played at it at 3 o'clock. There's no difference, right? It's the same kind of machine. Now, in the kind of like scheme of objectively when things happen, the signals of me speaking at 3 o'clock and at 9 o'clock are different. But they only differ by when they happened in time. So, me speaking at 3 o'clock is at some point in time. And then me speaking at 9 o'clock is at some point in time. So, they differ only by a shift. So in the same way that I define a delay operator to be a shift, you can imagine that waiting is like a shift. And then you say, all right, well, what if I use the toy now? I should get something similar. So this x of t becomes x of t minus k. And I would expect that this thing transforms it into the same signal, only now it's occurring later, because there's a difference again between the subjective time when things happen. So this signal would be my weird voice at 3 o'clock, and this would be my weird voice at 9 o'clock. So to compare them for like equality in the literal, this signal equals this signal, you'd also have to shift my distorted voice in time. So then I say, okay, well, let me apply delta k again. And the assertion is just that no matter which path I take, you should get the same output. In equations, this means that for any x that I choose, delaying and then applying the filter equals, well, applying the filter first and then delaying. If I drop x, it just means that these two operations commute. Both of these are filters, so you can say that these filters commute, but time invariance is a property of some filter you pick h, so time invariance means for any delay that I pick, it commutes with h. And that is the kind of second property that we're going to care about for filters. denoted Ti for short. So for each of these filters that I've kind of defined here, it'll be instructive if we can think about maybe what properties they satisfy. So for each of these guys, are they linear? And are they time invariant? So does anybody have any insight on which filters might be linear and what might be time invariant? You can come up and try it if you want.
Didn't we just show that delta k is linear and time invariant?
Well, time invariance for delta k kind of comes out pretty quickly because you can imagine what happens if I have delta k and delta L for some different number. It's like their action turns the thing into t minus k and then t minus L, but it doesn't matter which order these are in. So sure, delta k is going to be time invariant, but why would it be linear?
I was under the impression that delta k was just a linear map, so.
It is, isn't it? Right? Like if you add two signals together and then apply delta k, that's the same as applying delta k to one, applying delta k to the other, and then adding them. And then if you increase the amplitude and apply delta k, that's the same as increasing amplitude to the shift.
Yeah, so thinking about the linearity of delta k just means like, all right, so if I add two components in like my sequence of values, if I add these two things, it's the same as shifting them first or shifting and is it the same as shifting and then adding or adding and then shifting? And the answer is, well, yeah, they're kind of the same thing. So you can show this. What about amplitude? Changing the amplitude by a constant factor.
I'm gonna say linear and time invariant because it's just a scalar. It's just a scalar, and since this is a vector space, I don't think there should. I don't really see any like big issues.
Yeah. So an example of this would be like a megaphone for talking about time invariance. If I speak into the megaphone at any given point in the day, it doesn't really matter when I do it, it's going to have the same effect. So this idea of scaling the amplitude is okay. And you're right that kind of in the same way that the vector space operations were okay with the shift, they're okay again with scalar multiplication. Scalar multiplication like always preserves the vector space axioms. So what about squaring the thing?
It is time invariant, but it is not linear.
Yeah. So the general thing is that like every kind of example of squaring an operation, if I have two things added, I can square them, but that does not equal them individually squared. Because this is like the operation of the filter applied on each part, and this is the operation of the filter on like their sum. You always have this thing here, but that's not linear. And now what about this thing? Multiplication of your signal with another signal.
If the other signal is constant, it could be linear but not time invariant because the other signal would be dependent. Oh wait. No.
It's always linear, but it's not time invariant.
Yeah.
It would be time invariant if u was constant.
Yeah.
Okay.
And the vector k to x then won't be time invariant.
So, do you want to give me like a kind of mathematical reason for why time invariance doesn't work here?
I'm not sure how to do that. Like, I'm not sure of the formal way to explain it.
Well, so if I turn around and I start drawing like this thing, what we drew for time invariance. First, we start with the signal x of t. What happens if we apply the filter? You can just shut it out. Yeah. So you get x of t times u of t. What happens if I delay this result?
X of t plus k times u of t plus k, or minus k.
Okay. Now let's go the other direction. So x of t delayed is x of t minus k. And now what happens if I apply the filter?
So t minus k times u of t.
So there's a difference here now.
Do you represent all of these in matrices when you do computations?
No, you can represent these things as just long arrays.
Well, those are technically one-dimensional matrices.
Yes, okay. So, yes, you can represent these things as long 1/n matrices.
Okay,
You're
so
talking about
then
the signals, right? The signals can be represented as arrays, right? Is that what that's what you're saying?
Yes, yeah.
Yeah, but the transformations are not matrices.
No, in general, you don't do a matrices for this kind of single input, single output type of signal. You would just like iterate through each thing in the array, and you would like, in the case of something like this or amplitude changes, you would just iterate through it.
the only reason why I brought up the matrices was we know that it's not commutative. So I feel like that's kind of somewhat vaguely related to what you just showed in your diagram there.
So if you're working with a finite sequence of values, you can represent this thing with a matrix. But the issue is that
not finite.
we now have a countable number of coordinates, so trying to represent something like delta k with a matrix requires an infinitely big matrix. Okay?
Linear maps in this space still don't commute, by the way.
What?
Linear maps still don't commute on this space, by the way. He's just putting that as like a constraint, like they have to commute with a specific type of map.
Yeah. So specifically, time invariance is just commuting with only this shift operator, delay operator.
Okay.
So this example fails to be time invariant. So some of these examples are kind of not too difficult to think about, but there are ways to define filters that get kind of a lot hairier, a lot faster. So just for something to think about, which I'm not going to like fully divulge on now, is the idea of what a filter looks like with feedback. So what if I define a filter that at every point in time is equal to what the input is, plus what the input was before, plus what the input was before that. So this is an example of a filter which is not just described in like one instance of x. It's actually described in kind of an infinite number of elements here. It's described as this infinite sum of everything in your waveform, all of the data, and it turns out that something like this is still describable with linear time invariant filter. So this is something that's interesting to kind of do as an exercise. So now we have a notion of filters and we have a notion of signals. we can get into proving some properties about filters now that we've defined what the two big properties we need out of them are.
Hey Kurt, I have a question.
Yeah.
That's an infinite sum you wrote, right? With
Yeah.
YT. So do you run into problems if that sum diverges?
Yeah, but the only issue with it diverging is if you're trying to do something with a signal that you don't want to diverge.
Okay.
So it depends on what your choice of input signal is. In certain contexts, you might have a bounded signal. You might have something that is only defined after a certain amount of time.
Okay.
You might have a signal with compact support.
Okay, yeah, that would make sense.
So this thing is not defined for every signal, I guess. This would be an example of an unstable filter.
Okay.
And this is something that you're actually concerned with when you do control systems, which studies systems with memory and systems with feedback. Systems being another word for filter.
Okay.
Okay. So let's get into showing some things, please. So first, we need to make an observation about discrete time signals. That's just the idea that for any discrete time signal x, you can represent it using an infinite sum of both the deltas that we defined. So the impulses and the delays. So how does this work? Well, if I start by giving you a picture proof, it makes a lot of sense. So if I give you some kind of discrete time signal x, I want to start breaking it down as a series of impulses. I mentioned that in the beginning of the talk, each one of these blips is an impulse. So you can say, all right, well, I want to start breaking down x in terms of these blips. So I'll start with x equals 0. Well, I have an impulse that goes at x equals 0. That's just that's our definition of an impulse. But by definition, it has amplitude 1. So you say, all right, well, I need it to be whatever x was at time 0. So you just multiply that by x at 0. That's messy. Now, let's say I want to represent the next blip. Well, that would need to be some waveform which has an impulse, but shifted over by 1. So we have a way of doing that. That's just what we defined our delay operator to be. So we know we want a delay of 1 applied to an impulse, and again, it has amplitude 1, but we want it to be what x of 1 is. So you just scale this thing up by x of 1. And you do this again and again. So we do it for every single point in time. We add them up. And we get this idea that for any time-valued signal x that you give me, I can represent it in terms of an infinite series of all integers k, where I write x evaluated at each k times a k delayed version of the impulse. This thing is called delta decomposition, or an impulse decomposition. So, just one thing to note about this is that even though it's an infinite series, it's kind of well-defined because at any point in time that you give me, there's only one non-zero term. So the infinite series always gives me like a finite answer as long as whatever the value of x was at that time is finite. And since we kind of defined it that way, it works. So now, we've defined what the impulse decomposition is. Now I want to think about what a filter with the properties we care about, linear time invariant, does to this decomposition. So this is a theorem that for any linear time invariant filter that I pick, its action on a discrete time signal is kind of easily described. So this will make more sense again if we just start working with it. So take the linear time invariant filter H, apply it to X. Well, by that statement, it's equal to applying it to this infinite series. I'm going to move the function arguments down as subscripts now, just to be notationally convenient. So now we want to start simplifying this expression. The first thing we can notice is that H is a linear operator. This thing is acting on a sum or an infinite series. But in particular, at every point in time, this thing is a finite sum. So at every point in time, we can move H inside the summation, and we can use our properties of linearity to distribute. So at every point in time, we have this, where H is acting on these terms. Now, an important thing to notice is that x of k is x, the signal x, evaluated at k. It's a constant in this case because the only time varying thing is this delta, this impulse. So because this is a scalar now, we can again take it outside the action of the filter. And now, we remember that the other property we have of the filter is that it's time invariant. Time invariant is defined as being able to switch the order of these guys, so we're going to do that. So now, for any filter that you give me, I can compute what this is in advance. So you take the filter, you throw a single impulse into it. It's just that one blip. So you can imagine, like, if you're doing this as an experiment, it doesn't take very long. You just throw it in and see what happens. So if I just give it the one impulse, maybe it will take that impulse and like drain it a little bit. It'll give you some kind of echoes of what it sees at the output. In this case, we want to give this a name because essentially what this theorem is telling us is that we're going to be able to kind of add up a bunch of these. So we're just going to denote that by little h, and we're going to call it the impulse response because it's the response of the filter to seeing an impulse. 15 minutes. Okay. So we're just going to denote that as x sub k, delta sub k, h sub t. And now, I just want to define an additional bit of machinery just to make this notationally simple. So, an infinite sum of this style is equivalent to writing h of t minus k by definition. If you do enough algebra, you're going to see summations like this appear a lot. In particular, they go by the common name of convolution. And you can denote that with like an asterisk between the two things. So an infinite sum of this style is defined to be a convolution. And you might have some concerns about this sum being defined. And again, it depends on what h is. So under sufficiently nice conditions, this thing is going to be a well-behaved sum for any signal you give me x that's well-behaved. In particular, you care about like this thing being absolutely summable. So if I take the impulse response and I add up everything in the impulse response, does that give me a finite number? If that happens, then you have no concerns about what it's going to be doing here, just as like a kind of sufficient condition. Okay. So the theorem states that the action of a linear time invariant filter on a discrete signal x, h on x, is equal to convolution of this thing. And so now, just because we're running out of time, I'm going to start going a little bit faster. Are there any questions about that? All right. So before we can state the kind of major result here, we need another lemma. So this lemma is just that for any linear time invariant filter that you give me, we always know what the eigenvectors look like for it, or eigensignals, because we're working with signals. So the idea is that complex exponentials, something in the form e to the st, is an eigenvector of a linear time invariant filter. And so this thing's not too hard to see. If you just plug it in, say, okay, h to the st here, well, this thing is equal to convolution. If you start evaluating convolution, you're going to get something that looks like e to the st minus k, because you delay one component, times h sub k. So the convolution will give you something that looks like this. Now, if you imagine distributing the s, distributing the exponential, this thing is sitting alone. It's dependent on time, not dependent on k. This is a series of k. So I can pull this thing outside the summation. And so I get e to the st times this sum. But in particular, this sum only depends on what the impulse response is of the filter and what we pick for s. So I'm just going to compact that into another function, call it lambda s. But notice that this was the signal that we gave as an input. So it scaled that input signal by some number, lambda s. So that gives us that, well, the complex exponential was an eigenvector. And the eigenvalue depends on what we pick from s. Okay? So now we have this idea that complex exponentials are eigenvectors. It would be really nice if these things formed a basis. Turns out they do. So to show that, we have to invoke some machinery from either functional analysis or MET 341. So you can refer to like a textbook for either that class or that topic if you want to see like the full story behind this. So the process of representing a signal or a function in general in terms of complex exponentials is called a Fourier transform. Because we're working in discrete time, we're going to call it a discrete time Fourier transform, or DCF. So the Fourier transform gives you the coordinates of your signal in this complex exponential basis. In particular, what the Fourier transform kind of tells you is that the collection of these complex exponentials, where omega is any real number, tells you that it spans the signal space, where t is integer. And this kind of falls out as a result of this working in the continuous time case, and then when you do that conversion from continuous time to discrete time, it checks out. So you say, okay, how do I get the coordinates for this thing? The coordinates of a signal x are denoted by x hat. The x hat for each frequency that you pick, because this entire set is just indexed by whatever omega you pick here, is given by this like infinite sum. And you sum over all. So this is a method that gives you the coordinates of a signal in terms of complex exponentials. And so you can undo this process, and because you have a bunch of real frequencies, you integrate instead of taking a sum. But we don't necessarily need that to show what we're going to show. So just to state, the big result of doing all this work is a big theorem. And this is sometimes called the convolution of sequences, but specifically what this theorem states is that if I take the discrete time Fourier transform of a convolution, it equals or is identical to just multiplication of their individual Fourier transforms.
Do you mean isomorphic or?
No, like literally equal, because this thing is a function. This thing is a function of some real number r, and this thing. So convolution gives you a signal. Discrete time Fourier transform gives you now a function, and multiplication of two functions is a function. These things are like in the same space. They are like explicitly the same. And so showing this thing is not too bad. I'm just gonna like race through that. It's just the idea that if I apply this sum to a convolution, I get something that looks like this. Now I need to unpack the convolution. So you get a double infinite series. X of k, h of 2 minus k, e to the I omega of t, and then you add in another I omega for k minus k, just to do some algebraic trick. And you do some more stuff, and you eventually get the result that xk e to the minus I omega k times another sum h sub r e to the negative I omega r by, you do a substitution r equals xk, and you kind of more algebra. You get to this point, you realize, oh, well, this is the Fourier transform of a signal x. This is the Fourier transform of a signal h. They are explicitly equal. And you go through this whole procedure. So, what is the point of doing all this? Well, if I had a bit more time, I would have motivated it better. But the point of doing this is that computing a multiplication is a heck of a lot easier than computing a convolution in general. This thing gives you an infinite series. This thing just gives you component-wise multiplication at each frequency you pick, or each like time you pick. So this thing is a heck of a lot more like nice to work with than the convolution. And the reason why is that when you do like applications of these things, when you try to work with them in practice, you want to work with more than one filter at a time. So if I have like 2 filters in series, and I say, all right, well, I want to figure out what y looks like. Y equals g applied to h applied to x. Now, if I try to unpack this definition, it's the impulse response of g convolved with the impulse response of h convolved with x. But if I do discrete time Fourier magic, you get the idea that in frequency, this looks like y equals, well, g hat times h hat times x. And you can see, well, multiplication commutes, and you can compute like the multiplication of these two things. So you readily know what, like, in frequency, a filter that describes this entire interaction looks like. So I could like draw a bigger box around this thing, Q, and I immediately know what Q is supposed to do. And the beauty of this thing is that it works, it scales like in the exact same way. So if I now consider like more complicated systems with like feedback in the middle, and maybe it like adds the two together here or something and does more complicated operations, I can keep deriving what this thing is supposed to do, and it's really computationally simple. In this case, it looks something like y hat equals g hat h hat over 1 plus g hat h hat f hat x. And so this thing scales impressively well, makes a lot of computations possible, and this is mathematically how a lot of stuff is done in things like Photoshop and like audio engineering software, where you're actually applying filters all the time and you want to do it in a computationally efficient manner. This is the stuff that's going on in the background. And the only properties that you need to be able to do this is you just need to be able to say that it's linear and time invariant, which are not so uncommon assumptions. Any questions?
All right, thank you.